Mr. Chairman, for the introduction. Hello to everybody. The statement was we know that we do not know enough, and I want to add, let's say, some data and some learnings which we did out of some investigations in the last months. I want to speak about two subjects. One is the analysis of, let's say, running modern headlamp systems, also the power consumption which is taken by an ADB system in average, to learn about this. And then I want to switch to a second chapter, how we can reduce the power consumption by intelligent driving, the different lighting functions we have on the car. I want to start my presentation with a small overview and introduction, then speak about the ADB power consumption out of the ADB function. Then I will go to the illumination level and the correspondence of the road luminance, which is, let's say, for the adaptation of the human eye, the basics to decide which function should be activated and where we can do optimizations for the future. Then I have with me a small analysis about the activation of low beam and DRL for different illumination levels, and I will end up with a proposal for the energy consumption reduction. As a first picture and introduction, I brought with me a small selection of ADB headlamps which are running on the road today, different optical systems, different stylings and different performance levels which are active. And if we look to the statistics which is given and assumed by DVN, we see that the option rate or the numbers of ADB systems will increase in the next years and will reach in the European market about 50% of the cars. Therefore, the power consumption of this system is important and will, let's say, bring one factor for the overall power consumption of the car. So this is the motivation to have a look to these functions and their electrical power consumed. Here the first graph I want to show is a ride along a country road, out about 15 minutes, given here in seconds, 900 seconds, that means 15 minutes ride. And on the y-axis you see the electrical power consumption. For the low beam we have, let's say, a high-end low beam with more than 900 lumen on the road with more than 50 lux to the maximum, consuming 18 watt, including the ECU power losses. So this is the level of the low beam consumption. You see it here as one constant level. And when this system is jumping to the high beam, we are at 41 watt, the addition or the sum out of low beam and high beam power consumption. And we see here more or less, let's say, two different driving situations. Here when we see here in this chapter or this section, the 18 watt of the low beam power consumption, there's a car in front of the test car, and there is no chance to switch to the high beam. Therefore, the low beam level is maintained for this driving section. And the second section here, we see that there is no car in front, but there are oncoming cars, and there is a permanent switching between low beam and high beam. And there is, let's say, overall around about 3 cars coming from ahead during 1 minute. So even, let's say, a driving situation, the driver is not alone on the street. And when we now calculate the average of this power consumption, we see here around about 23 watt as an average power consumption for a low beam, high beam, which is switched automatically. So it's 5 watt above the 18 watt of the low beam. So this is the power consumption for low beam and high beam, which gives an advantage for the driver. It's switched very much more often than this usage factor of 3%, which is taken in this eco-innovation boundaries. And when we now take the same section here of driving and using an ADB system, we see a different picture. We see here now again the same low beam with 18 watt, and we see 45 watt for the ADB when it's in a full high beam situation, all segments are switched on. So the efficiency of the segmented high beam is not that good as for the standalone high beam, But we see here also in this section where in the graph before with the automatic high beam switching, no high beam was possible, that there are segments switched on. This 70% of switching on time of the ADB is realized in this system. So we see that the power consumption here is moving and is very dynamic, even there is a car in front of us because the segments right and left are switched on. And even in this situation where oncoming traffic is existing, we only come for a few moments back to the low beam situation or the low beam power consumption. Another question is, what is the average of these light distribution for this section? And you see it here, 33 watt is, let's say, the power consumption of this ADB system. That means we have, let's say, between the low beam, high beam system and the ADB system, let's say a higher power consumption in this section and also in this section here. And at the end, it's the difference of 10 watt, additional 10 watt for the ADB. That's not so much, because it's 10 watt in the ADB mode. You have to take into account also the urban situation, the low speed situation where the ADB is not activated. And if you take the average for all driven kilometers for the car, because this is only during nighttime, you will end up below 3 watt per headlamp. That means around about 5 watt per car per driven kilometer for when you take it on all kilometers as a statistic. So for sure we know that there is an additional power consumption which is needed, but it's a very good invest, because we know we invest this power consumption for safety. And when we look to the safety gain which we can achieve with the ADB system, you see it here in the HSPR effective performance rating. When you have a manual switching, we have an average range of 100 meters for the car. If we have the automatic switching, which are demonstrated, it's 10 meters more. And when we switch from automatic to the ADB, which takes in the ADB mode 10 watt per headlamp, we can gain again 15 meter main performance or average performance range for the car. And 15 meters means 0.4 seconds more reaction time in average to react on the driving situation or the traffic situation. So this ADB energy is a very good investment in safety, which we are, I think, all convinced of. But now we have figures how much is an ADB system, which has here, and showed it here, it's a one-row system with 12 segments, gives, let's say, this performance increase and the increase in power consumption. Okay, this is a current analysis of the current systems. Now I'm going back to the second chapter to make the analysis of the road illumination here on the x-axis and the resulting luminance which is achieved. And if we take here one example, 1000 lux on the road are resulting in 30 candela per square meter luminance level as an adaptation level for the human eye for the driver. And we have different regions. We have the headlamp only, which provides, let's say, a luminance 1 candela per square meter in maximum and below. So this is for the low beam only. Then when we have the street lighting, we have an area here which is larger. We achieve around about, let's say, 80 lux illumination level in, let's say, crossing situations where it is a, let's say, very high illumination level with 3 candela per square meter. So the street illumination gives in some areas much more light to the road and luminance to the road, results in luminance on the road in these street lighting scenarios. Then there is the twilight area, where the question is low beam switched on or DRL. I will show later on a small statistic about this. And then we have the daytime area also, let's say, with the cloudy sky here and with the bright sunshine with 100,000 lux on the road. And this, all these, let's say, large spread of illumination and luminance we have to take into account. for controlling our lighting functions. One investigation from Technical University says, what is the driver's need? What the driver wants to have in front of his car. And they made an investigation here for the driver's needs and asked them which luminance level is okay. And the luminance level between 0.8 to 1 candela per square meter is okay for 100% of the drivers. So this is, let's say, a target which we should achieve, and this, let's say, a headlamp alone is achieving, as I showed in the last slide. So 1 candela is, let's say, the target. And if we think about, let's say, low beam systems which is existing today on the road, we know such a system here having 7 LEDs on the road. We can, let's say, play with the foreground and the side spread and the range area. I can demonstrate here, you see here the light source with 7 LEDs for the low beam, the others are for the high beam, and when I switch on, let's say, the simulation of each single LED, you see this is the first one on the right side, and this is side illumination. The next one is for the side, the next one is for range, the next one for range, the next one for range, next on the left side for the left side spread, and the next also for the outermost left side spread. So this is, let's say, the option which we have technical-wise today, and we can group these LEDs. And technical-wise, they are in some modules also grouped, that we have, let's say, the foreground and the side spread on one electrical path and the range of the other one on the other one. So, and now it depends on the driving situation, on the illumination level, which I showed before, how we should balance between this range and this side spread. Depending on speed, depending on the traffic situation, with the cars nose to enter traffic or other, let's say, levels of illumination, we should think about to give to the driver the right level of lumens on the road, but we should not try to, let's say, boost 900 lumens, that means round about 40 watt to the road, if there is a street illumination which creates 3 candela per square meter. If only, let's say, 1 candela per square meter is okay for the driver, and when I have from the street illumination 3 candela per square meter, it doesn't make sense to put, let's say, 40 watt onto the road. 10 watt could be also okay per headlamp. Okay, the next idea here, where we made this small statistic and found out which is the activation level of the low beam, no, not the activation, the switch on of the low beam in comparison to the DRL as a function of illumination on the road. So we counted cars and we found out at 3,500 lux on the road, 50% of the cars are going with a low beam. And the other 50% are going with DRL. So with the low beam, rear lamps, dashboard, license plate, everything is activated and the full low beam. And with 3,500 lux on the road, we achieve 100 candela per square meter luminance level. So this is the adaptation level, 100 candela per square meter. And the headlamp gives 1 candela per square meter. That means 1% of this illumination level. So 50% of the cars are boosting 40 watt to the road, and nobody has any use out of this luminous flux and this power consumption. Therefore, the idea and the proposal is to, let's say, to adapt this switching and coming up to, let's say, the conclusion and the proposal. When we are looking and coming from the high intensities, 7,000 lux today is also the switching above the, so with 7,000 lux on the ground, the low beam has to be switched off in the automatic mode, and we have to switch to the full DRL. That makes sense. Question if this limit should be adapted a little bit, but let's say the proposal is to have between 500 and 7,000 lux an adaptive DRL. Because if we are on a low level of illumination, let's say like 500 lux, we should not, and it is not necessary to have the full intensity of the DRL. So perhaps at 500 lux, you want to switch on the low beam, the low beam here, because you want to have, let's say, some light on the dashboard. You want to have, let's say, a rear lamp on to be safe, to be seen, to be recognized on the road. This could be, let's say, the constellation for this area here with an adaptive DRL. Then below 500 lux, the proposal is to have an energy optimized adaptive low beam, depending on speed, depending on the street lighting and the traffic situation, and below the 30 lux to take the standard low beam. Summary here on the last slide. Today we are driving low beam or we're driving DRL. Only two lighting functions. And to have a little bit more intelligent split here, to have the low beam here for a small illuminations level, to have an adaptive low beam balancing range and the full flux, let's say, portfolio of the low beam in this area here up to 500 lux on the road. And on at 500 lux on the road, we can go up here and see here we are at 30 candela per square meter. So the adaptation of the human eye is not fully photopic with 500 lux. Therefore, it makes sense to dim down, because then we are more sensitive with the blue amount of the LED light. We are more sensitive to the recognition of the DRL. So we can here start with the DRL, which is perhaps, let's say, 50% reduced in power consumption, and then dim it up here until here to 100% when we are at a higher level of the illumination on the road. So to make it more intelligent, and then we will end up with a low beam, an adaptive low beam, an adaptive DRL, and a full DRL as we have it today. So there are options inside. We need more data to calculate and to find the arguments how much energy can be saved. But in this transition area here, with the adaptive DRL, we are in the twilight, let's say, adaptation. And in the twilight, we have it in the morning and we have it in the evening. We have it when there's a rush hour on the road. There are the most cars on the road and the most hours driven during this time. And therefore we have to need, let's say, we need more data, and we also will evaluate more data to find out, to quantify the effect if we try to, let's say, think about and work on it to have a common understanding of the power reduction in this field. Thank you for your attention.